We just got someone looking for the lights so we can get a bit more clarity on that screen. Just a little bit of background on me. I've had a long association with the soil. I'm going to try to make the connection between soil, carbon and action on climate change. My association with soil dates right back to when I was only a real little kid. I had a very rare disease that meant that I had to eat soil 3 times a day. And I've got my brother Tim to thank for alluding me to that fact that I had that problem. Have I got a clicker or something like that? So since we've all had a bit of food and our stomach bugs are all digesting away and taking the energy away from our brains and not to our brains, how do I get this expanded out? So there's no sound. Yeah, there we go.
Thank you very much. Sitting at home thinking about it, it's not good enough for me. I want to be a part of the solution.
Well, I truly believe that science is activism. Science is actually providing tools to fix a real world problem that needed solving yesterday.
So imagine a method that empowers farmers to take the carbon out of the air and put it into their soils on a gigaton, game-changing scale. A soil carbon capturing fungus, empowering farmers to become carbon capturing climate superheroes.
So a report from the front line. I'm an agronomist in Forbes, hour and a bit to the west of us here now. And this has been my experience for the last 4 years. 2016, 100-year flood. I managed about 20 growers down through that country. A lot of that crop went underwater. 2017, we had a full profile of water, got a heap of biomass away, and then we struck about 60 frosts in a row over our winter spring. That's just nuked a lot of canola and a lot of wheat. And then followed by 2018, that's south from the township of Forbes looking towards Lake Cowell. And a couple of weeks ago I got the pilot to take another photo this year facing roughly the same way. Spring's not supposed to look like that in Forbes. That's not the Tanami Desert. That's, safe farming country, regarded as in the past, historically. That's some canola a couple of weeks ago. It's supposed to be up hip height or better and flowering. Pretty disastrous sort of a season. So in my mind, that's what 1 degree looks like. So we're seeing all these things that are beating us because of the extremes. So the average is yes, it's only 1 degree, but it's pushing the climate around, so we're getting less rainfall, less often, more extreme events coming at us. And as growers, that makes it really bloody hard to grow food, as evidenced in my little district. So of course, it's not just Forbes, it's happening across the country. Of course, it's just not across the country, it's happening worldwide. There's the temperature record for the Americas, Europe, Africa, Asia and Pacific, going forward from 1905 to 1915. Some people are making nice T-shirt designs out of that. I think it's quite a macabre sort of a T-shirt design. Shows that temperature just increasing globally. So we've got to ask ourselves the question, do we tolerate, we've tolerated 1 degree increase and we're paying the price for that. Do we tolerate 1.5? Do we tolerate 2? Every tonne of carbon that's put up into the atmosphere, anthropogenic carbon, makes it just that little bit harder for farmers to grow food. Where do we draw the line? The IPCC, a massive global scientific effort to try to put some shape around this, what the problem is, how big it is and what we should do about it so governments can act in terms of policy. Out of that report, how many people have read that report, by the way, in the room? Great, so there is a few. So It's a pretty hard, slow read, and it's a pretty depressing read. But the three things that came out of it for me was that we have 12 years to nearly halve our emissions. So we need to think really big, and we need to think about scale and speed. Limiting global warming requires rapid, far-reaching, unprecedented changes. So we really need to think outside of the box. It's not just a gradual change that we're in here for. We need to really make big landmark changes. Emissions would need to be balanced with removing CO2 from the air. And that's the bit that, as an agriculturalist, that interests me. Can land-based solutions remove enough CO2 from the air to make a difference? So that IPCC report, to me, is like a smoke alarm. And we don't ignore smoke alarms. It's not being alarmist, it's responding to an alarm. So when a fire breaks out in a house, do you just go, oh, I think we'll just ignore that? Or do we ring the fire brigade and get something done about it urgently? We're on the stopwatch. If we think about it in terms of that 12 years, the IPCC has asked us to, or has indicated that we need to actually act with scale and speed. That puts us on a timer. We actually need to act fast. 11 years, 132 months, 4,000 days. A bit more sobering when you look at it in terms of days. The size of the problem. The size of the solution must equal the size of the problem. It's no good just these little, not using plastic straws. That's a great thing, but is it going to solve our plastic issues? It's the same with climate change. We need to look at scalable solutions, things that can be deployed at scale and at speed, which puts agriculture in a really good position, because as agriculturalists, we manage the largest terrestrial carbon sink on the planet, only second to the ocean. Soil carbon holds twice as much carbon as all the vegetation and all the carbon in the air. It's a massive carbon sink, and agriculturalists manage that on an annual basis. That's a heat map there you're looking at of all the annual cropping bread baskets, food baskets around the world. If you add up all those numbers, it adds up to about 550 million hectares of annually cropped farmland that we have access to manage in a carbon positive way. Which obviously makes farmers the world's largest climate army. All we need to do is work out something very, very simple and fundamental. How do we take the CO2 out of the air and stabilise it in the carbon, in the soil, sorry. We all know soil and carbon are two good things to put together. More carbon in soil equals more fertility, more water holding capacity, more nutrient holding capacity. Every 1% organic carbon holds somewhere between 180, 190,000 litres, 18 to 90 mils of rain per hectare per rainfall event, and about 20 units of nitrogen. In simple terms, we increase fertility. And that gives us the ability to scale at speed if we can work that one out. Because it's something that farmers already know about. We already desire more carbon in the soil. And when you look up at the sky and you see that colourless, odourless gas and think about there's 415 parts per million of a resource up there that we could actually use. Imagine if we could mine that, to actually take that out of the air and get it back down into our soils. That's money in the bank. How do we monetise that process, and how do we facilitate that process to happen at scale? So that's what's on the mind of all the team at Soils Quest. So we're sort of 15 to 20 people around Australia that made up of farmers and agronomists and soil scientists and microbiologists and a lot of other people working towards finding that sort of solution. So we look at all things soil carbon, integrated with farming practices. How do we build carbon into the landscape? Our Vanguard project at the moment is looking at a particular type of fungus, a soil carbon inoculum package, we're calling it, or affectionately we call it SCIP. That's some of the fungus growing on an agar plate there. So that's what it looks like when it's growing. So it makes a compound called melanin, which is the pigment into your skin, and it's a calcitrant type of carbon. So when you think of an analogue for this happening in the agricultural scene, we've already got an inoculum for pulling nitrogen out of the air and sequestering it into the soil. We call it Rhizobium. We've known about it for over 100 years. there's a global inoculum industry based on the fact of that little bacteria that lives inside those nodules is able to take the nitrogen out of the air and sequester it into the soil for plant use. What we're proposing is that there's a specialised fungus that does that job with carbon. We're simply taking the carbon out of the air and securing it into the soil in the same way. And you can see that micrograph there of a root with the hyphae extending out into the rhizosphere and sequestering that carbon, making melanin. That dark coloration in that hyphae of that fungus is melanin, a stable recalcitrant form of carbon. So that's what it looks like in the lab, something we've termed fungal mediated soil carbon sequestration. So the plant on the left is obviously the control growing in a sterile agar. The plant on the right is inoculated with one of our isolates that we're looking at, and that's a canola plant just growing there. So you can see what we're trying to achieve in the soil is that fungus growing and sequestering carbon, stabilising carbon into the soil. Both carbon from the plant flow and also labile carbon that's out in the soil volume. So it's bioconcentration of carbon. For the chemists amongst you, you're taking carbon dioxide out of the air, which has one carbon atom in that molecule, and then it gets turned into photosynthate or glucose through photosynthesis, which is C6H12O6. So you've got 6 carbon atoms. And then melanin is C18 into H12O4, I think it is. So you're going from 1 carbon atom to 6 carbon atoms to 18 carbon atoms by transferring the carbon from carbon dioxide into melanin. The recalcitrance of the compound is obviously of importance. It's no good putting carbon in the soil that can be exposed to oxidation and hydrolysis, which just breaks it down into carbon dioxide again, and it diffuses back out into the atmosphere in the carbon cycle. We need to make sure the carbon stays there. So one of the research focus on this particular compound is seeing, we know it's quite recalcitrant, we just need to work out just how recalcitrant it is. How many years can we rely on this compound staying in the soil? And that's just another pretty pic. So on the left is, in this time, it's lucin, and the left is control, and the right has another endophyte on it for lucin. And you can see in that one the lucin plants are actually doing visually a bit better than the control. So that's one of the things that we do when we're looking for these fungi. We make sure that they are actually beneficial to the plant host. So give an agronomic gain to the plant, early seedling vigour and more biomass and so on. So there's things that these fungi are doing that are similar to, for those that know about mycorrhizal fungus, that stretch out in the soil and for phosphorus and other nutrient acquisition and bring it back to the plant. These particular fungi, they're broadly known as dark septate endophytes. They're not actually a mycorrhizae, although some can be ectomycorrhizal. But we're looking for ones that give a positive plant response. So just a little bit of a graphic on how it works. So the plant makes photosynthate and the carbon goes down into the fungus, utilises some of that carbon, converts it into melanin and distributes it through its hyphae. And the fungus itself is very good at finding getting into soil microaggregates, and that's another part of our research is looking at where the carbon is being deposited. And the early research is showing that it's getting deposited inside microaggregates, and microaggregates are anaerobic at their core. So it's the perfect place in the soil to store carbon because oxidation doesn't happen where there's no oxygen. So if we can deploy that carbon back down into the soil inside microaggregates, it's safe for hundreds of years. So let's do some rough numbers around this. Is this a technology worth looking at, or is it way out as far as its scale towards the problem that we're trying to solve? How much could we scale something like this if we can get this research right? So cereals currently 731 million hectares globally. So what you're looking at in that slide is that root area there. And that's the engine room for carbon sequestration. So the plant's taking the carbon out of the air, taking some of it down into the root system, and the fungus is utilising some of that carbon flow to stabilise in the soil and prevent it from leaking back out into the atmosphere again. And that's what carbon dioxide flux, the flow of carbon dioxide from across 12 months looks like. And you see the colour change as carbon disappears. And this is the arboreal forest sucking down carbon from the atmosphere. And then as they drop leaves and that, the carbon goes back into the atmosphere. So this is the big global carbon cycle, if you like. It happens a lot in the Northern Hemisphere, obviously, because there's bigger landmass in the Northern Hemisphere. But the carbon flux controlled by vegetation is what I'm trying to illustrate here, how it moves seasonally. And so it doesn't stay at 450 parts per million static. It's like the earth is breathing in and out. And our croplands are responsible for at least some of that breathing in and out of carbon. So what we're trying to do is when the earth breathes in carbon, so in other words, when the crops are growing and sucking down that carbon, we want to stay in the soil, not breathe back out again as much. So let's do some numbers around that. So there's our humble fungus hanging off a root. This is actually one we prospected out west, but imagine that's a wheat root, okay? We'll do it on wheat. So imagine one single wheat plant and about a bucket of roots, and that one wheat plant, all we need to do is to get that one plant sequestering 3 grams of this soil organic carbon, this melanin compound, this fungal melanin, per plant. So imagine a halo of melanin being produced around that plant for about 7 months of the year while the plant's growing. It just has to do half a teaspoonful, 3 grams of melanin into that soil volume around that single plant. Then we look at how many plants do we sow per hectare. It's around about 1 million, give or take. A plant, so you multiply 3 grams by 1 million. Who's the mathematicians in here? I've used the calculator before. 3 tonnes to get the zeros right. 3 tonnes per hectare of soil organic carbon you could lay down just by this very simple fundamental process of putting the right fungus on this plant that makes that carbon thing happen. So then the world talks in carbon dioxide equivalents for trading and for to have a common language. So to convert soil organic carbon to carbon dioxide equivalents, we multiply it by 3.67 and we end up with around 11 tonnes of CO2 equivalent per hectare per year that we could pull down out of the atmosphere with just our normal processes. So we multiply that by how many cereals are grown on the planet. So say aspirationally we could get every farmer to do that, motivate every farmer to do that simple thing of inoculate his seed before he plants it into the soil and get that carbon sequestration thing going. You're at 8 gigatons a year. Over a decade, that's 80 gigatons. So if you divide that number by 3.12, that converts it to parts per million of carbon dioxide that's in our atmosphere. Getting heavy with the maths here. 3.75 parts per million a year. Getting up towards 40 parts per million over a 10-year period we could pull out of the atmosphere and put that valuable stuff back in our agricultural soils where it's going to be put to use for agriculturalists. So I've got about 3 minutes left. So I've just got a quick photo gallery here of what soil sequests do, roughly what we are. So we go out in some really hot, extreme climes. That's my 2 boys I took with me on a bioprospecting trip. That's about the only time that they're actually smiling. They were not that enamoured of Dad dragging them out the back blocks in 45-degree weather, except when we ended up the K-Bar pool that afternoon. There were smiles again. But that previous slide there, that we go looking for plants that are able to withstand heat stress and water stress, and they stand out in the landscape to us, and that's why we go out with Mad Dogs and Englishmen in 45-degree weather. That temperature gauge there is stuck 10 centimetres into the core of this old corkscrew plant, and he's still sponsoring green growth, and I don't know whether you can read it from there, that's 55 degrees C, 10 centimetres down into the root system of that plant. There's bakingly hot out there, and that little plant's going, I actually don't mind it out here, it's pretty nice. So we took an endophyte off that plant, and we've got some, that's the way we do it. So we GPS our point, and we take it back to the lab. We get a chap to do morphology on it and have a bit of a look at what it is. We sequence it, make sure that it's not a pathogen. We do all sorts of pre-work with it. Then when we've done in the lab, we go into glasshouse, obviously. This particular trial here was at the, we just sponged a bit of glasshouse space from the DPI in Orange. While they weren't looking, we snuck in there one night and set up a trial, more or less. And in that particular trial, we did a 7% increase in soil organic carbon in about 90 days, a little bit under 90 days. Now, they're unheard of figures for carbon sequestration, if anyone sort of can do the numbers on that. And then we go out in the paddock and trial it out in the paddock just to see with the practicality of putting it onto legume inoculums and various things to see how we can deploy this little fungus, get it inoculated onto plants and then go and check those plants to see if it's being colonised. And there's an enormous amount of scientific work. We're really at the start of our journey, and there's an enormous amount of scientific work to be done to really bear all this information out. We're certainly nowhere near being able to hand out sachets of spores and say, go away and sequester carbon with this fungus. Got a lot of work to do, but that's why we've set up this research institute to carry this research forward and just to see what we can achieve with this. Because if we're right, and this is actually possible to do this, we've got a technology we can deploy at scale, at speed, and of the magnitude that we need. So thank you very much. And that's my reason for doing it.
Thanks very much, Guy.
Thank you.